Well, hello, everyone. It's a real pleasure to be giving the Miller Lunch Talk. And what I want to use my time today is to give you an overview, sort of a big picture idea of where we're at in the search for dark matter, and also to contextualize where my work as a Miller Fellow fits into this landscape. Something I really want to impress upon you, though, is that in the last 5 to 10 years, this notion of the landscape over which we think dark matter could exist has been broadening enormously. And in particular, if we think of it as a dark matter as a fundamental particle, well, really the mass range over which it could live is 50 orders of magnitude, so an enormous range. One of the examples I'll tell you about that I've been thinking as what dark matter could be is this one I'm showing you at the bottom of the slide. And indeed, if you're not familiar with it, those balls that is making entry into the atmosphere there is actually a crystal, and I'll explain the connection later in the talk. But before I turn to telling you about this landscape, let me just step back and remind you about the problem of dark matter that I spend my days thinking about. In particular, at this stage in history, we have an enormous amount of evidence that dark matter exists. And if you've heard talks about dark matter before, you've probably seen many of these images and these pieces of evidence. But let me step back even further and tell you, where is this evidence coming from? And ultimately, it's coming from our faith in gravity as a force. And for example, one of the classic phenomena associated with gravity is the orbit of the planets around the sun, shown not exactly to scale in this animation here. And the idea with dark matter is that at this point in history, our faith in our understanding of gravity is such that even if we couldn't see the sun, just from the motion of the planets around the solar system, we would still be able to infer that there had to be something at the center that was pulling on them to keep them in that orbit. And although this isn't exactly what we see with dark matter in the solar system, at larger scales, this sort of thought experiment I just walked you through is actually why we think that dark matter is there. In particular, let me just talk about one of these pieces of evidence we have here, these rotation curves. And so this idea I just mentioned to you is sort of exactly what was done in the pioneering work of Vera Rubin back in the early 1970s, where what she did is she looked at our nearest neighbor, the Andromeda Galaxy, and she tried to measure how fast are the stars moving in that galaxy. And so what you can see in this plot I have in the top left is the speed of the stars, essentially as they orbit around the galaxy, and how far those stars that you're measuring are from the center. So we can measure how fast they're moving, but also we can make a prediction for, given what mass we can see, how fast should they be orbiting around. And the expectation is shown in the gray dash curve, and the measurements are well above that, as you can see in the data points. So for example, if I was to make a simulation of what we would think galaxies should look like just based upon the mass we can see, they should all look like the left animation shown at the bottom. But again and again, when we go and look at galaxies, they look like the right. And so what this is telling us is that our prediction for how fast these things should be moving is just wrong. And one way of fixing that is to add additional mass into these systems, but it's mass that we can't see, and this is dark matter. So after this pioneering work of Vera Rubin, there's been a number of additional threads of evidence that are telling us towards the existence of dark matter. In particular, as we begin to look at larger structures throughout the universe, everywhere we look, we seem to find dark matter. In particular, even if we look back to the earlier stages we can see in the universe, for example, in the form of the cosmic microwave background, even there we see that there has to be dark matter. So as a particle physicist, I say, well, I know what the answer to this problem has to be. We just need to take all the particles we know about and add one more, and that's what's going to solve this dark matter problem. So you might think that's a bit of a stretch. I'm telling you that there's this offset at like the scale of galaxies, and you're telling me that something on the subatomic scale is what's going to fix this problem. But to remind you, it's not as crazy as it might initially seem, because everything else you can see in these images we know is made of particles. That's the great success of the atomic hypothesis. And sort of the miracle of particle dark matter is that you can just add, in many cases, one particle to those we know about, and you can make all of these various observations consistent with our theory. So just another thing that we get from these pieces of evidence, there's many things we can learn about dark matter, but I think one that is relevant for the talk today is that if we just add up how much mass is in the universe, the majority of it is in dark matter. Actually, it's like 84%. So we've made enormous strides in science, and particularly in physics, in understanding the universe and the world around us. But in terms of understanding matter, we only know what 16% is made of. 84% of the matter in the universe, we just don't know what it is. So this seems like an enormous hole in our understanding. Potentially, you could even characterize it as an embarrassment. But I think flipped around another way, the way I would say it is that I think the most exciting discoveries about what dark matter is lie in our future. And today I want to give you a landscape about where we think those discoveries might end up occurring, or where the current thinking is related to that. So I've told you that I think dark matter should be a particle. Well, where would you go and learn about particles to see what we know at the moment? Of course, the relevant place to go is the Particle Data Group book, which is essentially the Wikipedia of particle physics, which is a book where we compile all the different data we know about the existing particles. So for example, if you open the PDG to the entry for the Higgs particle, which is one of the most recent particles we've ever discovered back in 2012, you'll see there's a huge amount of evidence we have related to it. And for example, one of the basic particle properties we know of, the mass of the Higgs boson, we know that very accurately. You can see here, it's about 125 GeV, or about 125 times the mass of the proton. Okay, let me ask the same question of dark matter. A very fundamental property of a particle is its mass. What is the mass of dark matter? The answer is we have almost no idea. Despite the fact that this is just one of the most basic properties you would want to know about a particle, and despite our enormous confidence that dark matter is a particle, we don't know what that mass is. And indeed, as I'll show you today, this mass could exist over 50 orders of magnitude, and you could still come up with a consistent theory for what dark matter is. Now, why I think this is a very interesting and fundamental question is because at the opposite ends of this spectrum, dark matter would behave dramatically different. At the very lightest end of the scale, dark matter would behave essentially as a quantum state at the size of galaxies, whereas at the very heaviest end of the spectrum, dark matter would almost be a macroscopic object. It would be a particle with micrograms of mass. So I'll walk you through some of the ideas that we've been thinking about for what dark matter should be, and also, again, I'll focus in on some of the things I've been working on in this landscape. So before I go out to this full 50 orders of magnitude, let me just go back and tell you sort of what this rule of a particle mass that I'm introducing here. Throughout, I'll be using units of essentially electron volts, or here GeV, which is a billion electron volts, to measure mass. And that's just because it's convenient, because a GeV is about 10 to the minus 27 kilograms, which is a pretty small number to be carrying around. So throughout, when I'm looking at this ruler, I'll always put lighter particles to the left and I'll put heavier particles to the right. And let's start out this ruler by putting on one of the particles I've already talked about, the Higgs boson. We know that's roughly 100 GeV, so this is one of the heavier particles we know about. We'll put it up on the right. What's a lighter particle we could put on the same ruler? Well, for example, the proton. We know that's about 1 GeV, and that would be much lighter than this Higgs particle. But now when we want to add in another one, for example, the classic electron, we know the electron is about 2,000 times lighter than the proton. So immediately you can see this is going to be way to the left off this plot here. And pretty quickly, even for the particles we know about, trying to fit this onto a linear mass axis is going to be impossible. So let's just move over to a logarithmic scale. So what I'm showing you here is, again, the Higgs boson and the proton up at the heavier end. But now every notch on this ruler corresponds to 1 order of magnitude of particle mass. And every of the larger notches corresponds to 3, where there's an associated SI prefix. And we'll be working through most of those throughout today's talk. So just to show you where the particles we know about are, again, the proton and the Higgs are at the heavy end, the electrons down at about half MeV. And then even within the standard model of the particles we already know about for sure, we do have evidence that at least one of the neutrinos must be at least 0.1 eV, so way down at this lighter end here. And although as I go forward in the talk, this range that I'm showing you here may seem small, I want to impress upon you that I think it's quite remarkable that even the particles we know are spread across 12 orders of magnitude. And to be honest, it is still an open question as to exactly why that is fundamentally. Also, just let me quickly contextualize this mass range I'm showing you here. For example, down at this EV scale, which is a bit heavier than what we think one of the neutrinos will have as mass, is where the full optical spectrum would sit. So the energy of a photon that makes up light would be sitting around the EV scale. Or if we go up to the heavier end, we're looking at sort of the highest energies we've ever been able to probe in a terrestrial experiment. For example, the Large Hadron Collider, we've managed to reach energies of around 10 TeV. So we're sort of really spanning a huge range of energies here also. Good, so now let me use this mass range that I've talked about for the particles we know about in the world around us and sort of show which dark matter candidates lie in this space. And it's going to be the ones that I would call the dark matter classics. So these are sort of the basic, the really dominant ideas that have existed in dark matter for the last 40 years. In particular, probably the most popular or well-known dark matter candidate is the so-called weakly interacting massive particle, or a WIMP. So this has a particle mass that runs from about a GeV to a TeV. So very similar, for example, between to the proton or the Higgs. One other fact that will be useful later on that I put in the top right of the slide here is actually from these same gravitational measurements I told you about earlier. We know that there should be some dark matter near us here on the Earth. Actually, it turns out that because we can measure the mass, if this dark matter particle had a mass of a proton, about 1 GeV, then there would be 1 dark matter particle per centimeter cubed. So this is a significantly smaller number than, say, Avogadro's number, but there's, you can imagine that there's sort of this gas of particles flying around that maybe you could hope to detect. There's actually many different ways that you could think about looking for these WIMP particles, and actually there's been experiments going since at least the 80s trying to find them. My favorite way of searching for WIMPs is the following line of reasoning. Given that these particles exist near the other particles we know about, we would expect that they should be able to also undergo the types of interactions that the known particles do. And one of these interactions is that when matter meets antimatter, we know can explode into energy. Similarly, if dark matter particles meet anti-dark matter particles, they could explode into energy. And if this is happening throughout the universe, then we can go and look for this extra energy beyond what we might have expected otherwise. So for example, if this dark matter is in this GeV to TeV range, you can figure out, well, what would the photon energy be that comes out of this annihilation process? And it would be in the gamma ray range. So you want to go and use a gamma ray telescope. So let's go look out at the universe in gamma rays and see what we find. And famously, actually, there's a long-standing anomaly here that may be associated with dark matter. So this is something called the galactic center excess, which was discovered in NASA's flagship gamma ray space telescope, the Fermi telescope. And essentially, it's just many more gamma rays are coming from the center of the Milky Way than we would think just from conventional astrophysics. Now, is this the discovery of WIMPs? Unfortunately, it's just not clear-cut, and probably I would think the field is thinking at the moment it's unlikely. It's more likely this emission is associated with millisecond pulsars. But it's a challenging problem, and we're still trying to figure this out, and it's something that I've been working on for a long time, and also as a Miller Fellow. But certainly nothing definitive at this stage, but it's a very enticing signal. Let me tell you about another one of the dark matter classics. This is something called a stellar neutrino. So the neutrinos actually are almost great dark matter candidates because they don't interact with light. So they satisfy that defining characteristic of dark matter. Actually, a very good dark matter candidate, though, would be a heavier neutrino called a stellar neutrino, which would have a mass in around this keV to 100 keV range. Now, there are several different ways of looking for stellar neutrino dark matter, but one of them is we think that these stellar neutrinos should occasionally decay. Now, this decay has to be very, very rare because, as I showed you earlier, we know that dark matter has existed for essentially cosmic history. So if it decayed too rapidly, it would have disappeared, and that's not consistent with the observations. But even if it has an exceptionally long lifetime, there's so much dark matter out there that you might occasionally be able to spot this. And it's thought that these stellar neutrinos would decay into a photon, and if they have a mass in the keV range, this would be an X-ray photon. So again, there's been a number of experiments going out and looking for these X-ray photons coming from where we think there's dark matter. And what was an exceptionally exciting discovery back in 2014 was Bulbul et al. And collaborators claimed that they have seen a line associated with this dark matter decay process. So this anomaly became known as the 3.5 keV line. And again, initially, it looked like it may be the discovery of dark matter. So this was a question, I mean, of course, if this is correct, it's one of the greatest discoveries in particle physics. So it's something a lot of people have been thinking about. And in my time as a Miller Fellow, I was really trying to think about ways we could put this to the test. And with some collaborators, we developed an extremely sensitive analysis to this type of line. So if dark matter is doing this, we found a very optimal way of seeing this signature. And when we unblinded our analysis, you can see in the black crosses here, these are showing what the data was. Our best fit background only model is shown in the solid red. And if the dark matter had been decaying to these X-ray photons, we should have seen data consistent with the red dash curve. Now, in our paper, we do some statistical analyses, but I think you can see by eye that what we're seeing here is just not consistent with the 3.5 keV line being associated with dark matter. So this work, I think, in my mind, comprehensively rules out that particular anomaly is associated with dark matter, but that is not the statement that is on everyone's mind. If you want to read about this a bit more, I can link you to, for example, this article here. There's actually been a fair bit of back and forth in the literature where people have been quite critical of our work, predominantly those people whose model we rolled out. Now, I don't think that any of the objections that they have raised have lead me any reason to believe that we had any errors in our original analysis. But I think that this dispute that is going on is more sort of gives you a picture for where we're at with the dark matter classics. There are some hints that maybe we've seen something, but there's definitely been nothing definitive. And after 40 years of searching, there's been every opportunity for the WIMP or the stellar neutrino to show up in our experiments, and they just haven't yet. So this has really, I think, catalyzed a mindset in the field of maybe we're just not thinking about dark matter the right way. Maybe it could be something completely different, and this is why we haven't seen a signal yet. And so this is what is going to give rise to this exploding of the mass range that we look at, which I want to mention to you in the last part of my talk. To begin with, let's go low. Let's think about dark matter particles that are much lighter than the ones I've been talking about now, or indeed much lighter than any of the known particles we're aware of that have mass. So the first, in order to do this, I just want to introduce one more concept associated with particles, and that is that due to quantum mechanics and wave-particle duality, we know that all particles, in addition to having a mass, have essentially an intrinsic wavelength or spatial size associated with them. And it's defined such that the lighter the particle, the larger the scale. So this is going to become relevant quickly as we go to the lighter dark matter masses. Also recall that I said that if you have a dark matter particle that's about 1 GeV, then you have about 1 per centimeter cubed. If I start making the dark matter lighter and lighter and lighter, I now have many, many particles per centimeter cubed. And also their spatial scale is getting larger and larger. Eventually, these particles are going to start overlap, and any attempt to describe this, this gas of particles as like individual states becomes essentially not particularly useful. Instead, you want to transfer over to thinking about this as more of a wave. It's a very similar transition to what happens when you go from, example, gamma ray astronomy, where you think about the photons as discrete particles, down to radio, where you think about them as waves with much lower energy particles. The transition for the case of dark matter is expected to occur for dark matter masses around 10 electron volts. And so for dark matter much lighter than that, you really should be thinking about it as a wave rather than a gas of particles. In particular, as I said before, we know that there should be dark matter near the Earth. And if the classic hypothesis is that this dark matter is like a gas of particles, and this is what we've been looking for. But if in fact this dark matter is much lighter and behaves like a wave, well, now it becomes very clear why we haven't been able to see any signal of it so far, because we just weren't looking for a wave. So let me tell you how you would discover dark matter if it was a wave. And let me do so by mentioning the real classic wave dark matter candidate, which is the axion. And if you're wondering, yes, it is actually named after the laundry detergent. So axion dark matter is predicted to couple to the stuff we know about in the following way, with a modification to Maxwell's equations. So I'm showing you here on the right slide the classic Maxwell's equations in the black here. And in the presence of an axion, you get an additional term to Maxwell's equations, which is this red term on the bottom right. In particular, what you can see is that if you have a large magnetic field, which is the B there, this will couple to this axion, which is A. And remember that this dark matter is a wave that is undulating, and so it will convert this magnetic field actually into an effective current, which you can see by analogy to the J term, which is there in the fourth equation. And so the idea then is that if you manage to set up a very strong magnetic field in the lab, you may actually be able to detect some effect associated with this if the dark matter is made of these axion waves that are passing through your experiment. So this is an idea, although it's been discussed for a long time, really the experimental search for it has only begun to explode in the last decade. And in particular, one of the instruments that are looking for this is the abracadabra experiment, which is actually an acronym. And this instrument is a very powerful magnetic field, which is currently in the basement of MIT and has been running for a number of years, starting to take data searching for this dark matter hypothesis. And it's a collaboration I'm a member of. So although at the moment we really haven't scratched into the surface where we think we could detect dark matter yet, what the point of the abracadabra experiment has been so far is just to set up that these type of detectors could even work. And so far, all the signs are that they will. And so now there's a lot of thinking that in the next decade, we'll build much larger versions of these instruments that really will be able to find dark matter if it is one of these axions. Also, I just want to give you a flavor for the fact that this really is sort of an area where there's lots of developing thinking. And so, for example, there's some basic things if you think about waves that have actually been overlooked in the literature when it comes to talking about dark matter as a wave. In particular, something else, especially in astronomy, that is often used exploiting the fact that light is a wave is interferometry. And so if dark matter is also behaving like a wave, well, then we should be able to perform interferometry on it also. As I said, in the near future, we expect that there'll be a number of experiments located around the Earth trying to measure these effects associated with dark matter. As my collaborators and I showed late last year, you can take this data and you can actually perform interferometry directly on the dark matter wave. Now, you might ask, why would you want to do this? And the answer is, if you're starting to see some emergent signal, but you're not sure whether it's dark matter or it could be some background you didn't anticipate, well, actually, dark matter with interferometry imprints a unique signal on this that you can help determine that you're actually seeing a real effect of dark matter. In particular, these instruments will be rotating through the dark matter wave throughout the day because of the fact that we know that the Earth orbits on its axis every 24 hours. Because of this, you can actually get information about what direction the dark matter wave is incident on the Earth. And so what I'm showing you in this sort of heat map on the left here is the best guess position as to where the dark matter is coming at on the entire sky. This is a mole-weed projection of the full celestial sphere. So you can see at the moment, there are some places you can rule it out, but there are tons of places where it could be coming from. But this is just using one time slice, essentially, or one moment in time of this data. What we'll find as we add more data throughout the day, we'll actually be able to break the degeneracies, as I'll show you in this animation here. And eventually, through the use of this interferometry information, we can actually essentially localize where we think the dark matter is coming from in the sky. And because we actually know where that roughly should be, because we know the motion of the sun through the Milky Way, we can confirm whether what we're seeing is consistent with dark matter or whether it's something else. So dark matter can get much lighter than axions even, however, but it can't just get arbitrarily light. At some stage, remember that these particles have a scale associated with them. Eventually, it'll just become bigger than galaxies. And we know that galaxies exist. So at that point, whatever you're talking about, I mean, maybe it's something interesting to think about, but it can't be a particle that's the dark matter of our universe. So this is an idea that's called fuzzy dark matter. I don't work on it specifically, but actually it was an idea that was really popularized back in 2017 by former Miller visiting professor Jerry Oestreicher and collaborators in this paper here. Something I have been working on, I'm very excited about, however, is going right to the other end, thinking about how heavy can we make this dark matter particle. So let me do away with the SI prefixes. There was a bit of a squeeze to get them on here. And now what I'm showing you is all the way from this lightest end, this 10 to the minus 22 eV, all the way to where we think about how heavy could dark matter really be. Is there a limit to that if we're thinking about it as a particle? And actually there is. And where this limit comes from is, I said that every particle with mass has an associated scale, which is this lambda dm I'm showing you here. Further, if I have some mass restricted to some part of space, actually, there is another spatial scale associated with it, the event horizon of an equivalent mass black hole. And so what happens is that if I make the dark matter mass heavier and heavier, the event horizon gets bigger and bigger, but the particle size gets smaller and smaller until it collapses into its own event horizon. And there is no longer any notion of talking about this as a particle. What you have is a black hole. Now, actually, black holes could be dark matter, and then you could think about objects that are much, much heavier than what I'm showing you here. But in my research, I focus on the hypothesis that it's just a fundamental particle. And if that's what you're doing, you have to draw the line at 10 to the 28 eV, which is what I'm showing you here. Okay, so if dark matter is one of these super almost black hole massed objects, how exactly would you go about searching for it? Well, again, actually, we think that it could do some of the things that normal particles do. Like the neutron can decay. We think that these heavier dark matter particles would actually decay. And when they decay, through E equals mc squared, they would release an enormous amount of energy just because they're so heavy. So at 10 to the 28 EV, you can calculate this is actually 1 billion joules, which is about the same amount of energy as released in 500 kilograms of TNT exploding. So there would literally be these explosions happening throughout the universe that you would go and look for. And these explosions would be depositing their energy into fundamental particle interactions. So you'd have like a proton or an electron flying out with obscene amounts of energy. In fact, so obscene that you can go and calculate that these protons, for example, would carry about the same amount of energy as a cricket ball bowled by Shane Warne. So it's like a macroscopic object is carrying the same amount of energy of one of these fundamental particles. It's a really remarkable thing. And the way you would search for it actually is that these particles, when they hit the atmosphere, would create sort of an explosion or a shower of other particles that you then go and search for on the surface of the Earth. But I won't go into detail in that here. So actually, this idea that heavy dark matter could explode was sort of something that had been discussed for a while, but what was missing was a real quantitative picture. I mean, you can go and tell experimentalists that there are these very energetic particles that are exploding throughout the universe, but you really want to tell them what exactly they should see in detail so that they can go and determine whether your hypothesis is correct or not. So this was actually something that people had some ideas about, but they were very unsure about how to calculate it in detail. And actually, it's something that I turned my attention to as a Miller Fellow and had some work really showing how to do this correctly that came out last year with these collaborators at the bottom of the slide. So what we wanted to do is we wanted to figure out, you inject this crazy amount of energy into fundamental particles. How do you do the quantum mechanics or the quantum field theory calculation for determining how that energy is then distributed amongst the many particles that could be created? So what I'm showing you here is the slightly technical outcome of these results. And so on the left, for instance, or in both plots, I'm showing you on the x-axis the energy of the particles that comes out. But for convenience, as I'll explain in a moment, I'm showing you the energy as a fraction of the mass that was there to begin with. Because the mass tells you how much energy was injected, and so I'm sort of telling you what fraction of the total energy that was injected is carried by one given particle. On the y-axis, I'm showing you how many particles carry that particular mass. And so essentially what this is the distribution of particles that comes out. In orange, I'm showing you the distribution of photons that's expected to come out from one of these processes, and in blue, the distribution of neutrinos. So existing results had tried to calculate this, but they're only able to go generally up to about 10 to the 18 eV, which is 2 eV that I'm showing you here. And there, they had the predictions that's shown in the dash curves, the orange dash and the blue dash. The results of my collaborators and I are significantly different from that. You can see that the y-axis is logarithmic, and so we predict that there is much more emission coming out of these processes than there was expected otherwise, and we believe there's good reasons to believe that our calculation is much more accurate than what existed previously. Further, what's very satisfying about our results is we don't need to stop anywhere. Previous results really didn't work above, I said, about 10 to the 18 eV, but the Planck mass, this black hole-sized mass, is 10 orders of magnitude higher. So how do we get up there? And with our results, we're able to just crank the handle, do the calculation, figure out what happened. And what I'm showing on the right is, as I inject more and more energy by increasing the dark matter mass, what happens to the spectrum? And so this is where it was very useful, the fact that I'm showing it to you on dimensionless units, so that all I'm showing you is how the energy is repartitioned as a function of what fraction of the total energy it's taking. But you can see we can go all the way to this MP, which is this 10 to the 28 electron volt shown here, whereas previously results had to stop 10 orders of magnitude below. So this was a huge improvement in terms of our predictive power for what these things should look like. Okay, but now we have the results. We need to go and do the search, and that is work in progress. But let me end there. So what I've sort of shown you today is that dark matter, although we have a huge amount of evidence that it exists and we know a lot about it, and I really do believe it's a particle, it's sort of shocking that this fundamental parameter of a particle, its mass, is so poorly determined. It really could live anywhere over the 50 orders of magnitude. So again, you could almost frame this as sort of an embarrassment, like how are we so ignorant that it could live over this enormous space? But again, I have a very optimistic view of this. I think the fact that we're really challenging our classic ideas about what dark matter should be and really thinking originally about where it might show up means that we may have just been thinking about it wrong so far, but these new experiments may actually be finally able to resolve this mystery. In particular, I think that these axion particles are very well-motivated candidates, and some of these experiments that will come online in the next 5 to 10 years have every chance of discovering what dark matter is. Okay, so let me end the science portion of my talk there, and I just want to end with some acknowledgements. I want to thank the fantastic collaborators I've had in my time as a Miller Fellow who helped me on the work that I've shown you throughout this talk. I'd also like to thank my Miller host, Lawrence. Of course, not just this talk, but everything we do at the Miller wouldn't be possible without the fantastic support of Hilary, Donata, Emily, and Vrinda, so thank you so much for that. And then also, certainly, a lot of the polish that is in this talk today, I mean, I'm hoping there is at least, was provided by the feedback from Yong, Hector, and Michael. So thank you so much to them also. Let me end there. Thank you for your attention.